Today we're going to be talking about fluid statics. We spoke about mechanics with forces and torques, acceleration, angular motion. We've dealt with the deformation of solids when we dealt with elasticity. Then we talked about scaling. Now we're talking about fluid statics. So what's a fluid? What's the difference between a fluid and a solid? If you put a solid into a container, like a bunch of marbles into a glass, the marbles stay in the shape of marbles. They're solids. If you pour some water into that glass, the water takes on the shape of the glass. So one definition of what a fluid is that it takes on the shape of the container that it's in. So from that perspective, fluids can be either liquids or gases. Now, what's the difference between a liquid and a gas? A liquid, you could say, hey, a gas is transparent. Yeah, but water is transparent, right? There's nothing to do with it. Liquids are incompressible, just like solids. So when we did elasticity, we found that when you apply a stress on the solid, you get a very small strain, right? Meaning a very small deformation. The volume changes very little. Okay, it's relatively incompressible. On the other hand, liquids, are also incompressible. So if you try to apply some forces on some water and try to change its volume, it would resist. It would not change its volume. The density stays pretty much constant, regardless of how much forces you apply on it. Gases are different. You can change the volume of the gas. When you put the gas into a container, it will fill up that space. And if you make that container twice as big, it'll fill up that space. The density goes down. Okay, so in gases, you get large variations in the density. That's a big difference. Okay, so when working with fluid statics, we're going to have to introduce some new concepts and new formulas. And the first, so just like we were working with F is equal to ma in classical mechanics, and force was so important, when it comes to fluid statics, it's going to be pressure. So it's the pressure. And the pressure is written as the force per area. So if, for example, we have a container of water, you're going to have at every single point in that container, there's going to be pressure. Okay, so what's pressure? Pressure is due to the bouncing of all of these little molecules off you, let's say. Okay, so you're going to feel the pressure on the walls of a vessel or something like that. And the definition is the magnitude of the normal force per unit area. So every single time a molecule bounces off of a wall, that causes some force. So pressure is a very complicated thing. Like, for example, you can feel the temperature in a room, and when the temperature changes, hot or cold, you feel that, right? Pressure is something we tend to ignore. We're just accustomed to the pressure, the atmospheric pressure around us. But we notice what we really can notice more is changes of pressure. And so, like, for example, if you jump into a pool and you swim deep into the pool, you might start feeling, once you start getting to the deep end, you start feeling the pressure of the water around you. Maybe if you're driving in a car and you go up a hill or up some high slope, you start feeling your ears pop. Or, oh wow, let's say you're in an airplane, right? If you've taken an airplane, your ears pop as the pressure in the cabin changes. And so what you're really feeling is a change in pressure. And what's happening is the pressure outside has changed so quickly that the pressure inside you hasn't followed. And that's why your ears pop. Okay, if the pressure changed slower, you would match that pressure, and you wouldn't feel it. Okay, so we're not very good probes of pressure. Okay, we're probes of pressure change. Okay, so pressure is sort of funny that way, because we're not very good at feeling it and measuring it. Now, the way to think about it is that if there's like a little point in space, there's pressure there. And the equation is going to be force per area, okay? So there are different units of pressure. So the unit that we're going to be using for all of our calculations is typically going to be pascals, and that's newtons per meter squared. That's the same units that you saw in Young's modulus, right? But it is just a coincidence. It's newtons per meter squared. We can call that a Pascal. There are other units, okay? Other units, and a very common one and a very practical one, okay, is the atmosphere, ATM, atmosphere. So 1 atmosphere is 1.013 times 10 to the 5 Pascal. And that's just the definition of an atmosphere. And that's the pressure that we typically have around us. And, you know, when the weather changes, it changes a bit, but that's the standard. 1 atmosphere is that. And you'll sometimes see it written down as 101.3 kilopascal. Be careful, okay? It's nice and easy to work with the K. And you might think, well, you work with kilograms, so should we work with kilopascal? No, okay? You work with kilograms, meters, seconds, newtons, Pascal. The kilopascal is just a shortcut to not to have to write that times 10 to the 5, for example. Now, 1 atmosphere can be written in Pascal, and there's a conversion. And another unit is called the PSI, and that you've seen that if you've ever filled up a bicycle tire or a car tire or a soccer ball or something like that, you're going to see that it might read fill it up to 30 psi or something like that. And 1 atmosphere is 14.7 pounds per inch squared, or psi. Next. So, I'm going to show you this whole slide. The bottom line is what's important. And what it says is if I or you swim down into the depths of some water, you're going to feel a pressure increase. And that pressure increase is going to be equal to rho GH, the density of the water times the gravity, acceleration of gravity, constant, and h, the height difference. Okay, the difference in pressure that you're going to feel from, let's say, the top of the water to the bottom of the water is going to be rho GH. And here's the derivation for it. Okay, it's in the textbook. Okay, I'll explain quickly how it works, okay? The derivation goes like this. You have a body of water. Imagine a little subset of that water in this fictitious shape. Let's call it a cylinder. And this is sort of a mathematical proof to get that equation at the bottom. So since this volume of water isn't moving relative to the other, it's all standing still, we know that the sum of the forces has to be equal to 0 on the collection of water right there. And so the sum of the forces has to add up to 0. And let's say sum of the forces, and I'm going to say up, down. Okay, the up-down forces, I don't know why they're so sloppy, has to add up to 0. And so we can say the pressure at the top is acting on the top surface area, and the force on the bottom could be described as the pressure at the bottom, okay, times the area. And we can't forget the mass times the gravity of our collection of water molecules, mg. So then you write that down, we redefine, we say, hey, but the pressure at the bottom, can't we just call that equal to the pressure of the top plus a difference in pressure? Why do we do that? Because then we can cancel out the pressure at the top, and we eventually just simply get this. Okay, very nice. Whenever working with fluids, you don't, although you might start off with something like a mass, we're going to realize that the mass is always equal to the density times the volume. So we subs that in, and we get this. Okay, then, and this is sort of a nice trick, we know that the volume of the cylinder volume is equal to the area times the height, right? So that means that that the volume over the area is equal to height, right? So someone can substitute that, and so we get the difference in pressure from top to bottom is equal to rho GH. That's how we got this equation, and that's the hydrostatic pressure difference equation. Okay, and this, from some perspectives, is our like F is equal to MA, starting point for fluid statics. So how do we use this equation? Delta P is equal to rho GH. So here's, you're going to open up the textbook and you'll see there are all sorts of examples that sort of look something like this. And what it is it's a water vessel, and it's got some channels and height differences and stuff like that. And the name of the game is going to be figure out the pressure at different points in this picture. And if you can do it, it means you understand what's going on. So, for example, what's going to be the pressure here at this point over here? We're going to call this P1. What's going to be pressure P1? How are we going to figure it out? Okay, well, it's the first time we're doing it, so I'll explain how we do it. The first step is to realize that the pressure outside, okay, we know it. What's the pressure outside? It's 1 atmosphere. Okay? It's 1 atmosphere, which is equal to 1.013 times 10 to the 5 Pascal. Okay? We know it. The way we use this equation, delta P is equal to rho GH, is it tells you the difference in pressure due to a difference in height. The difference in pressure due to the difference in height. Okay? So if we know the pressure outside is 1 atmosphere, or 1.013 times 10 to the 5, what's the pressure right here, by the way? It's the same. Okay? Okay? Why is it the same? It is. Okay? It's connected. It's not moving relative to the air. It has to be at the same pressure as the air. It's the same height as the air. It's the same pressure. So that's the starting point. So can we figure out what the difference in pressure between this top point here and the bottom point is? Yes. Oh, it's going to be rho GZ is going to be equal to the difference in pressure. Okay? And wait a minute, which pressure is going to be larger? Okay? P1 or pressure outside? Well, remember, you're swimming down, okay? Down lower, okay? As you go down, the pressure increases. So we know that the pressure 1 is going to be larger. And so we write that down. Boom. P1 is going to be equal to 1 times 10 to the 5 Pascal plus rho GZ. And so this is important. Wait. Okay, important because we went down. Okay, that's important to understand. Okay, next. So what's the pressure in the next point? Right there, let's say, P2. Pressure 2. We're going deeper into this vessel. So I guess the pressure is going to get more, right? Well, let's think again. We know two pressures in this picture now. The pressure outside, well, we know the pressure right there at that interface. We also know the pressure here down below, just a depth of Z. And what's the difference between the pressure P1 and P2? Okay. P2 is equal to P1 since delta, or let's call it, since, right, H is equal to 0 between them. Does that make sense? There's no height difference between them. So because they have no height difference, they're at the same pressure. Okay, makes sense. So P2 is the same, is the absolute pressure, or atmospheric pressure plus rho gz. The third point. Can we figure this one out? P3. So, well, we know the pressure at P2. We're going to use the pressure at P2 to figure out what P3 is. Okay, so P3 is going to be equal to P2, right? And then there's going to be this rho G Y. That's the difference in pressure between P.3 and point 2, right? The question is it going to be plus or negative or minus? The answer is minus, right? Because we went up. That's what's important. Okay, so we can spell it out, and then it works out that pressure 3 is going to be the 1 atmosphere, and then it's going to increase by Z, okay, and then decrease by Y. Okay, rho G. Next one. Ooh, this point over here, let's call it P4. What's the pressure in this point in air, okay, that's above, well, inside this chamber? We're not given the distance, but I'll tell you something. All of the pressure here, okay, is at P4. And you know what? This here, that's P4 also. All of these points, okay, are all the same pressure. And so we'll realize that, okay, P4 is equal to what? Well, let's see, it's equal to P3, right, minus rho Gx. Does that make sense? Yeah, it makes sense. Okay. So it's equal to that. I mean, you can also calculate plus Z minus Y minus X. P4. Next. Last one. I think it's the last one. P5. So, the picture didn't have an arrow. It doesn't tell me the dimension, the distance from 4 to 5. So how are we going to figure it out? Oh, I see. What we realize is that it's the same height as P1 and P2. So P1 is equal to P2 is equal to P5 because they're all at the same height. And since they're connected by a water, right? It's not like they're in a separate chamber. They're still connected by water, okay? They're going to be at the same pressure. And so that's that. Okay, I'm going to erase that. And we'll stop right there. Wait, almost stop right there. We'll keep on going. So a little more. Okay, we're going to talk about absolute versus gauge pressure next.